Hello again. In this video, I want to try to show you how to solve these problems when you're calculating. So what you'll see here is I have drawn on the board one of your problems. If you look at your sheets, I have numbered this one number 1 because it is the 11 volt, and so for the source voltage, and it has a 5.6 for your base resistor, 5.6 k ohm. And so that's the first one I'm going to be doing. It is up here. I did put these in a straight line, so perhaps I'll have enough room to actually come in here and show the formulas for these while I'm working them. I actually stopped here. If you'll see that the IRF right here, all of these plus this were on the second column on your sheet, so you'll see that they would be over here. And I write really big, and I have a really small board, so I'm going to try to keep these going. The one thing I will also say is just because they're starting with IRB and going on down doesn't mean that they will be solved in that order. Sometimes they're different. So what I will do is I will try to number as I'm going through, and some of these will already be given for this where some won't. So on this particular problem, I want to know that I have the 11 volts for my source voltage that's applied. My collector resistor or collector load resistor is 3,632 ohms. On the collector, when I measure this value right here, this value here, and this value, all three are measured from ground. So I put my ground clip here, touch with my red lead, touch with my red lead, and my red lead. So my collector voltage is 8.7 volts, my emitter voltage is 1.8 volts, and my base voltage is 1.9 volts. So then from there I can go ahead and calculate and determine what these values are. And again, this is for DC biasing. I am looking at the questions that it asks, and I can tell you right offhand, the first one that I know that I can answer is the type of transistor, number 1, because that is looking whether it's an NPN or a PNP. And actually it's not pointing in, so it's an NPN bipolar transistor. And the main thing I'm looking for here is the NPN. So the second one that I would look at would be my forward biasing, because if I'm looking at this one, I want to look and see what I do and don't have, but on my forward biasing, I know that that is the drop between the emitter to base. So if I take the 1.9 and subtract the 1.8, that's the 1.9 volt minus the 1.8 volt, that will tell me that that forward biasing is equal to 0.1 volt. And knowing that it's a 0.1 volt and it's in the range for a germanium, then this tells me that this is a germanium transistor. So we've done 3 problems really, really fast. Then I would start looking at it and try to determine what do I have or what don't I have. And so when I look through this to try to figure out, what I do and don't have, I know I don't have the IRB. It's not given to me, and this current's not. But if I come down here, I can actually see that the voltage across the emitter resistor here, the base resistor is given to me here. This one right here is given because this is in parallel to it. So if this is 1.9, that's that 0.1 plus that 1.8, that tells me that this is in parallel and it's a 1.9. So it's really given because it is equal to the base voltage. And I'm using the E's, because of the paper has the E's on there. Remember, it's E means voltage just like V does. So that's the one that's given to me next, and that would be number 4. I would look to see, I also am given this one, which I'm going to call it number 5, because 5 is the collector voltage. Well, that's the one taken from the ground to the collector, and that is given. I'm just picking ones out that are easy to get because I know I'm going to have to solve for other things. And that is given as the 8.7 volts. still looking to see what else I could come up with easy or I have given. I don't really see anything else given, but I do see that this one here would be pretty easy to solve, and that's that voltage across the collector load resistor here. So I'm going to call this one number 6 here. And so I know that it's the source voltage minus the collector voltage, which is that 8.7. So in that particular case, the 11 volts minus the 8.7 volts is equal to 2.3 volts. I'm going to go back now and kind of look, because I've kind of gone all the way down. I can do this one as well. This would be number 7 if we wanted to. And that's the emitter to collector voltage. That's the one from here to here. Well, I do know that the voltage from here to here to here equals the source voltage. But I also know that this voltage plus this voltage equals that voltage. So if I say that if I take my collector voltage minus my emitter voltage, that would give me the one between the emitter to collector. So in that particular case, I could take that 8.7 volts minus the 1.8 volt, and that would give me my 6.9 volts. I'm going to come back up to the top and see, because now I have solved some things here, so is there something that I can do up in here? And actually, I could do some things here. And coming back up this way, I would look at number 8 here. And I know number 8 is my voltage drop across here. And I've determined already that this was a 1.9 volt plus this value would give me 11 volt. So in this case, 11 minus that 1.9, because this is kind of parallel to that. So in that case, I could say my source voltage minus the voltage drop across RB, which is equal to the base voltage. So that's the 11 volt minus the 1.9 volt. Should give me the voltage across there, which is the 9.1 volt. On my, this one here is my current. I have a voltage now across there. I'm sorry, I have a voltage there, but I don't have a resistance, so I'm going to have to work on some other things here. So we'll come back to that one in a moment. I don't have my collector or my base current, so I don't want to do this one. RF, I have a voltage, but let's just keep coming up and see what we can come up with. IRB is the current through RB. Oh, I could do that one. So we're going to do that one as number 9. Because I know that the current flow is the voltage divided by that resistance. So if I have the voltage across RB and divide it by the resistance of RB, and I'm going to put that in here as RB, that's going to equal the 1.9 volts divided by the 5.6K ohms, and that will give us our current of 339.3 approximately microamps. Now remember, your amp meter is not going to measure real precise, so I'm not really too worried if it's 339 and a third or something like that. That's good enough for me. Now, we could also do, the next one is the current here. So I'm just going to come over here and say 10, because I have the voltage drop and the resistance. And again, we probably could have done this earlier, but I went ahead and did some easier ones first. So I'm going to go ahead and say that this is equal to that voltage drop across the emitter divided by the resistance of the emitter. That will equal that 1.8 volts divided by the 2.7 k ohms. And that is going to equal 339.3. Oh, what did I do? That's RB. I'm sorry. That is going to equal 666. I don't know how to multiply or divide here. And it's going to be 666, so you can put it as 666.6 or 666.7, which is what I used here. And that is going to be in microamps. I can't do the base current yet because I don't have a voltage drop there for the base, because that changes. But I do have enough information now to get the collector current. So I'm going to go down here to 11 and call the collector current, because I know the voltage drop across the collector load resistor, which is, and I can divide that by the resistance of the collector load resistor. So we found out earlier that this value here is actually equal to, I lost my place here, to 2.3 volts. And that is divided by the 3,632 ohms. And what we will find there is that's equal to 633.3 microamps. Now we could actually come back in here and do IB, because IB formula we said was actually at one of the other videos, we said that IB equals IE minus IC. So when we look at that, we can say that IE was 666.7 microamps, or 6 if that's what you used, and IC is 633.3 microamps. So that is going to equal, and I didn't give myself enough room in here, so I'm putting an arrow here. It's going to equal 33.4 microamps. And I've got a light that's shining in there, so let me see if I can tip it so you can see it a little better. Okay, it is going to go right back in there, and I know that, but that's okay. So that was 12. We're still kind of stuck with RF, but we do know the voltage for RF, don't we, is going to be 9.1. And so we also know that we could calculate RF now, I think. Let's come down to it, because we don't have that one yet. And this would be number 13. This one is going to be the current flow through IRB and IB. So in this case, this would be the current through RB plus the current through the base. And we determined that IRB was 339.3 microamps. And we determined that IV was 33.4 microamps. So now we know that that is going to be equal to 372.7 microamps. And that last number may be 373 or something like that. I mean, you can round it up some if you round them all up. So now we have the current. We already said we had a voltage, so this is going to be number 14 that we saw, because we're going to use Ohm's law, ERF divided by IRF. And so you said the voltage drop across RF was actually equal to 9.1 volt. And it's going to be divided by that current we just found, which was 372.7 microamps. So when you divide the current into the voltage, you should end up finding that that's about approximately, and I just rounded mine up, 24.4 km. Now notice that that's a very big resistor. It usually is the biggest resistor, so we can reduce this current down. When we look at just individual resistors, this one here has a pretty big voltage across the transistor and this resistor when we look at the collector, but for the resistors, that's usually your biggest resistor, and this is normally your smallest one. Notice I said normally. It's not an always thing in the book. And then the last one we don't have is number 15, and that's our beta. And we remember the formula from some of the other videos was actually my collector current divided by, let me write this a little different so we can see it. It's divided by my base current. So my IC, you said earlier, we said was 633.3 microamps. And that will be divided by that 33.4 microamps. And the gain of this transistor should be about I'm trying to do it in my head. It should be about 18.9 or 19. I think it comes out 18.9 the way I have it, or you can just put 19. And there's not a measurement on that because it's just a ratio. And that's the way we would work these problems. When we look at number 2, 2 has negative values. So what you would do is remember that only the voltages are negative because of our meter orientation. We're going to be putting our common lead on the ground, and then that makes our red lead here, so that gives us a negative value. It just tells me that the current is actually flowing in the opposite direction. The best thing to do is to solve this. Just pretend like there's no negative signs there. Just apply negative signs to your voltage at the end. Because when you put an ammeter in here, you're actually going to put it where the current flows from negative to positive through the ammeter to keep blowing up your ammeter. Yes, it just means the current is backwards and the voltage is backwards, but we don't want to hook it up into the meter backwards for the ammeter. It has to go into the following polarity for your ammeter. This is the one I call number 2. This is the one I would work on next if I were you. And just solve it like we did this one. But just remember at the end of it, just put the negative signs in front of any voltages. The third one doesn't appear to give you enough information. And so what I just want to say is on that one, Remember how in the videos before I said that the current is going to be somewhere between 3 to 5% for the base and 95 to 97% for the collector. So you could do a couple of things here. You can say, okay, you'll be able to calculate your emitter current. So then you could go in there and say, okay, the emitter current's here. So you could take the 3 or 4 or 5% for your base of your emitter current, or you could take 95, 96, 97% for your collector. Just remember though, if you use the 5% for your base, then you must use 95% for your collector, because 95 plus 5 equals 100. We must equal 100% of the current, because that's what flows through that transistor. What goes in must come out through 2 different paths, and they must total. So that's the way you would want to solve that one. If you have any questions, please let somebody know.